Last one, let's go. Get my screen right. Woo. Good. All right. Polymorphism done. Final exam coming up. Those of you who need to take it, you should know who you are. If not, I suppose you could send me an email to confirm. I might send out emails to everyone just to confirm what you'll be doing with the final exam. If you don't have to take the final, I'm not even going to send you an email during the final. And if you have to take one or the other, I'm only going to send you an email with the links that you actually need. So if you don't get an email for the final exam, that means you didn't have to take it. But I assume everyone knows where they're at with that. So let's just jump into this. And if not, I'm here for questions. Oh. Okay. All right. Let's do this. Graphs. Whoa. I blanked on my... There we go. Blanked on my keyboard shortcut. Okay, so we've talked about a variety of data structures up until this point in your career between 115 and 116. We have our sequential data structures, which is our array, which we used array list in 116, and our linked list. These two data structures keep a sequence of values, meaning that the order matters. So if I insert the values 5, 20, and 3, I expect those values to be in that order in the data structure. And arrays had random access. Linked list did not, but linked list could change size, and we can manipulate the structure of the linked list very easily, where we can't manipulate the structure of an array very easily. We have to create a new array and copy all the values over. So two sequential data structures, a key value store. This is where order doesn't matter anymore, and instead we're creating an association. We're associating keys with values and storing our values at those keys. Then we saw our first nonlinear data structure. The latest one that we saw was a tree, and specifically a binary tree, meaning that there are at most 2 child nodes for each node. And this was our first nonlinear data structure, meaning the data is branching off in different directions, and we saw that that gives us some nice log n runtime properties as long as we have a balanced tree. And we can represent different types of information. One thing we could do with this is a decision tree. Like I mentioned with the 20 questions example, we can do a decision tree where each node is making a decision and going either left or right, and then eliminating half of the nodes of the tree each time we make one decision, which is a very powerful thing. It's what gets us our log n efficiency. And then we end up getting data like this. So with those data structures in mind, what do we do with data like this? Where we have, right here we have New York City's subway stations, subway lines, which are subway stations connected by lines, and stations are connected by lines. We have roads, which are effectively intersections that are connected by roads. And the smallest example here, the one where it's small enough to use for a lecture example today, is the very, very early days of the internet, where we have multiple locations connected by cables that are acting as internet locations. I want to say routers. I'll just say routers. Routers on the internet, and they are connected by cables to other locations that are connected to the internet. This is the very early days, just the handful of major universities connected on the early days of the internet. Before it was even called the internet, this was, I believe, the ARPANET days for this diagram. Okay, so this is the example we'll use, and we have this kind of data where we have information that's connected to other information, and it's a very nonlinear structure that we have here. So we only have one nonlinear data structure. So we want to represent this data in our data structures. So given the data structures that we know, array, linked list, key value stores, and trees, which one are we going to use to represent this information? And of course, the title of the lecture gives away what we're actually going to use for this. But let's try to use trees first. So let's use a tree. Let's just pick one of these nodes as the root of the tree. I'm going to pick UCLA. And all of the other nodes are going to be child nodes of that node. And we can't use our binary trees anymore, so we have to use something else. I think it's called a multi-tree. But anyway, a tree where the nodes can have any number of child nodes. So we'd have like an array list of child nodes. So we have all the child nodes of UCLA, which is every location connected to UCLA on the graph. Oh, and I'm already spoiling it. My mind's just thinking ahead here. But all the other locations connected to UCLA as child nodes. And then for each of those child nodes, we have to get all the connections to that node. So let's go to Stanford and repeat the process. Stanford, SRI, and UCLA. So we'll have those two as child nodes. And we have a few issues already here. Stanford has UCLA as a parent and UCLA as a child. We have duplicate data in our data structure. So we need some way to handle this. And with this specific situation, you might say, okay, just add a conditional to say if that node is your parent node, don't add it as a child. So we can handle that one. That's not too big of a deal. We get rid of this problem. The other problem is a much bigger issue. So Stanford has SRI as a child. Stanford doesn't have SRI as a parent, but SRI is in the data structure already. So every time we add a child node, we'd have to look through the whole data structure and try to find out, okay, do we have that data in this data structure already? Okay, we do. We have SRI, and then the question is, what do we do about it? Because if we have a tree, if we're representing a tree, we want to capture this information that Stanford and SRI are connected, but we don't want to duplicate SRI as a node in this tree. So what are we going to do? I don't know. We're not going to use trees is the answer. We're not going to use trees. So this is a problem because this could go infinite if we're not careful, that we have lots of duplicate information in our data structure. We don't want that. So what we're going to do instead is, instead of creating a new node for SRI, we're going to have Stanford refer to the SRI node that already exists. So we create a reference to that existing node and then do that throughout the entire data structure. So every time we have an edge to an existing node, just draw in that edge. Just draw in that connection. And this is the data structure we're going to use. This is how we're going to represent data of this type. The problem with this is it's no longer a tree. We kind of started with the idea of a tree, but this ain't no tree. This is no tree. And the difference, the big thing here is that a tree cannot have any cycles in it. Cycles are not allowed in a tree. So the fact that UCLA has Stanford as a child, which has SRI as a child, which has UCLA as a child, I guess, I don't know, it all just breaks down if we try to think of this as a tree still. But we can't have these cycles. You can't go from one node and follow these connections, which we're going to call edges soon. Follow these connections and get back to that node with more than two nodes, because you can always go down one connection and then back, and that happens in trees and that's allowed. But we can't have these cycles where there's at least three nodes where you can travel the path and get back to where you started. That's not allowed in graphs. Or in trees. Once you have that, you are no longer a tree, but we can just call it something else. We're going to call it a graph. So graphs are like trees, except cycles are allowed. You can have cycles all day in graphs, and that's perfectly fine. That meets the definition of a graph. And in fact, every tree is a graph. And once you have a cycle, it's no longer a tree, but it's still a graph. So for a little technicality, on that. That'll be more important in like 331 when you take that, if you're taking that, knowing that, and 250, I guess, knowing that every tree is a graph. Okay, but we have some problems. So one, how are we going to represent these graphs? That'll be the next thing we'll talk about. But also, how do we work with these graphs? Those are actually our two big questions that we're going to spend the whole lecture talking about. Just like our other data structures, it doesn't take long to talk about what the data structure actually is, the structure of the data structure, but talking about how to actually work with that data structure, that's what's going to take the longest time. So none of our algorithms that we learned for trees are going to work, which were our traversals. We really didn't do much with trees. Our traversals and binary search trees, BSTs. But our traversals aren't going to work. We can't even just visit every node exactly once using our traversals because they're going to get stuck in infinite recursions. You're going to have UCLA, which is going to visit Stanford, which is going to visit SRI, which is going to visit UCLA, which is going to visit Stanford, which is going to visit SRI. You're just going to get stuck in the first cycle that you find and just blow up your algorithm. You're going to go infinite at that point. So we can't use our traversals. We have to use something else. And first, we have to actually just represent this data. How are we even going to put this data in our code? So representing the data, we're going to drop the structure that we've been talking about for linked lists and trees and represent these graphs in a completely different way, which is why I'm not sad that we lose a graphs tracing quiz because they're represented so differently anyway. It's really not the same topic. But nodes and edges, this is how we're going to represent them. So nodes, we're used to that from trees. We called these nodes already. The objects that stored the data, I guess entities, I can't call them objects right now, that store the actual data. And then edges that connect two nodes together. So there's an edge connecting UCLA and RAND, and we don't have any direction for that edge. Whereas with trees, there was a clear parent-child relationship. With graphs, there no longer will be any concept of that. There's no root node of a graph. It's just this blob of information is a graph, and no node is special. No node's a parent node of another node. Instead, we call these neighboring nodes. If these two nodes, they're connected by an edge, so we're calling them neighbors. And they're on equal footing. Neither one of them is special. Whereas with trees, the parent was special. The parent was storing a reference to the child. We don't have that directional information in our graphs. There are directional graphs. We're just not going to talk about them in 116. If you took 191, you should know all about that. In 250, you'll talk about directional graphs and all kinds of different graphs. In 116, we are talking about bidirectional graphs only, meaning that the edges can be traveled in both directions. So with all those technicalities out of the way, we're going to represent these graphs with nodes and edges, and we're not going to use references like we did with linked lists and trees. We are going to store a collection of all of our nodes and a collection of all of our edges in separate, actually just one data structure in our code. We're actually only going to use one data structure. And we're going to represent this. There's two different major primary ways to represent graphs. There's an adjacency matrix, where you have a matrix where the rows are all of the nodes and the columns are all of the nodes. And then there's a one or true for any cell. Is that what they're called in matrices? Any cell that has an edge connecting those two nodes. So if I had all of the nodes as columns here as well, and there's a edge between UCLA and Stanford, I would go UCLA, go to the Stanford column, and put an X there, or a true, or a 1, or however you're representing them in your graph, to say that there is an edge connecting those two nodes. That one, in other courses, you'll talk about that. You'll deal with adjacency matrices more, and explore all the pros and cons of adjacency matrices and stuff. We're only going to see adjacency lists. This is what we're going to use in 116. It fits our needs more, and we only need one way to represent graphs. Like, we're really not trying to dive deep into graphs in 116. I want you to know what a graph is, and then get your hands on it in task 8 and learn how to work with a graph. That's our goal in 116. so we don't really need both of them. But adjacency matrices, they exist. If you've seen them already, great. If you haven't, you will see them if you're once you take a few more computer science courses. What we're going to use is an adjacency list. So for each node in the graph, we're going to store a list of all of its neighbors. So for UCLA, it has 4 neighbors: Stanford, SRI, UCSB, and RAND. So for UCLA, we're going to store Stanford, SRI, UCSB, and RAND. And true for every node, SDC has neighbors of Utah and RAND. So SDC has neighbors of Utah and RAND. So we're representing all of this information, which we're representing visually and spatially right here. We're turning it all into one data structure that when you look at this, hopefully you can start seeing how we're going to represent this in our code. We're going to have one data structure, which is going to map nodes to a sequence of other nodes, which in our code, this is going to be a hash map. We're going to map these keys to these values, where the values are going to be array lists of nodes. So that's how we want to represent this in our code. That's what we're heading towards on the next slide. But first, notice that every edge in this graph is in this adjacency list twice, which does capture the information that you can travel these edges in both directions. If these were directional graphs, each edge would only show up in this adjacency list one time. But we can go in both directions. So this Stanford to SRI, for example, from Stanford you can get to SRI. From SRI you can get to Stanford. So every single edge is in this data structure twice to capture that bidirectional nature. So if you want a directional graph, say you can only go from Stanford to SRI, but not the other way around, then this SRI to Stanford, you would get rid of this one, but you would keep this SRI to Stanford, Stanford to SRI, but then remove the SRI to Stanford. You wouldn't have that one. Okay, and in the code it looks like this. I'm just going to hit you with all the code. This is my only slide with code this entire lecture. We will go to IntelliJ at the very end, but this is the only slide where we're talking about code. So let's hang out on this one for a little bit and make sure we know how to use this graph. This is the graph class from the repo. Excuse me, for task 8. You're welcome, as always. Just grab the graph class. I would expect you all to just use the graph class that's provided. There's no reason to recreate that functionality. And just use this graph class. And then call this add bidirectional edge, or add edge. No, that was in the... I'm getting my homework assignments mixed up. But add bidirectional edge is going to add those edges in both directions that we had, like we just saw. So here's our adjacency list, a hash map of nodes using a type parameter to an array list of nodes. That's how we're representing all of the nodes and edges in this in this graph. When we create the graph, we're going to initialize that adjacency list. And then when we add a bidirectional edge, meaning we want to add an edge that's going in both directions between these two nodes, these two neighboring nodes, we're first going to do something where we lazily initialize the adjacency, the array list, the adjacency list for each node. So we're going to call add node on both of those nodes. What add node is going to do is check if we've seen this node before. Check if the adjacency list contains that node. And this should look familiar from your task 6, where you're checking, have I seen this song before? If I've never seen it before, initialize it. And then no matter what, if it's just been initialized or if it's been around forever, we're going to process the information for that node right now. But if it's the first time we've seen this node, we're going to initialize our adjacency list, put it into our hash map, that node that we're adding, and a new array list because it has no edges yet. So initialize each node. If they've already been initialized, add node just doesn't do anything. Because it's already been initialized, we don't want to overwrite all of the edges that already exist for that node. So we're not going to remove any information. But if we've never seen it before, we want to initialize that data structure. And then finally add in these edges, the edge information. So the adjacency list, get the array list for node 1. We know that exists. We know we will never get a key error here because we just called add node, and if it didn't exist, we just initialized it. We just created it. So we know this is going to give us an array list, and we're going to add node 2 to it to say node 2 is a neighbor of node 1, and vice versa. Node 1 is a neighbor of node 2. So we're going to get all that information in our adjacency list, and then when you're using a graph, create a graph and call add bidirectional edge. It'll go through all this stuff for you and add all these edges into your data structure, into your adjacency list of your graph. So you can start working with this information, working with this graph. We also have an add edge method. You shouldn't call this one. If you see this code in the repo where we're only adding the edge in one direction, then don't call that one. Don't use it. Oh shit! I gotta take a quick break. I forgot to feed my dog breakfast. I'll be right back. All right. Sorry about that. I heard him crying out there. He's starving. So you create your graph and call add bidirectional edge a whole bunch of times. That's how you're going to get your graph. And I just got to check one thing because it's driving me nuts now. I think I'm thinking of the wrong thing, but I just want to double check to make sure. Yeah, add bidirectional edge. Okay. And you're going to want this get adjacency list method as well. So once you create your graph and add all your edges, you're going to call get adjacency list in your code. That's how you're actually going to work with the data that you have in your graph. So this get adjacency list method also is going to be very helpful. The rest of these, we created these for lecture examples that we don't use anymore, but left the code in here just, I don't know, it's good to have more examples, I think. And add edge, we don't use this these days either, but we left it in the repo. But creating the graph, the constructor, creating the graph, calling add bidirectional edge, and get adjacency list, those are the three methods that you're going to want to use. Outside of that, you don't really need any of the other ones. Okay, so that's the code. That's how you're going to use a graph. And that's it. We're done with code until the very end, where we should have a little extra time at the end that we'll go over some, do some live coding. If you're looking at the slides, by the way, the third set of slides is a memory diagram. Since there's no quiz on graphs, I'm not going to bother with that memory diagram. I think it'd be a waste of time. I want to do live coding because that will better prepare you for task 8, which you do actually have to do, instead of preparing you for a quiz that doesn't exist. I think live coding is a much better use of our time. So let's get a definition out there. A path in a graph is a sequence of nodes where each consecutive pair of nodes is connected by an edge. So this UCLA to SRI to Utah to MIT to BBN to RAND, all of those moves were following an edge, meaning that is a path in the graph. SRI, Utah, BBN, SRI to Utah to BBN. There's no edge between Utah and BBN, so this is not a path in the graph. So a path, each adjacent node is connected by an edge. Which will be an important definition going forward. Okay, and that really is graphs. That's the structure of a graph. That's how we're going to represent them in our code. That's the methods we're going to call to use them. That's graphs. The rest of the time, we want to talk about breadth first search, BFS, breadth first search, which is an algorithm we're going to use to traverse our graphs. It's similar to our traversals of trees, except we're actually going to get more information out of this breadth first search. Just like how we have adjacency matrix and adjacency list, but we're only going to use adjacency list. There's also depth first search and breadth first search. We're only going to look at breadth first search in 116. You will see the other things in other classes. You will see those before you graduate. But in 116, we just need the minimum viable product. What do we need to know about graphs to get the job done, which is task 8. Oh, I didn't introduce task 8. Maybe I'll do that after the slides. Task 8, where we're figuring out the... I forgot what it's called. I keep calling it Bacon number, so that's what it's used for, but... I forgot what it's called. That's bad. I don't know. But using our movies.csv, given 2 actors, how many movies do you have to traverse to get from one actor to another? It's going to hit me what it's called. Can't believe I'm blanking on what it's called. But how far away what 2 actors are in terms of starring in movies together with other actors. And let's define connected component. The connected component of a graph is any subset of nodes where every node in that subset is connected by a path between those 2 nodes. And if the entire graph is one connected component, that means the graph is connected. So this is a connected graph because no matter any 2 nodes that you choose, you can always get from one of those nodes to the other using the edges in the graph. No matter where we start, no matter where we end, we can get from every node to every node by following edges. This is a connected graph. But if we drop 2 of these edges, I just deleted 2 of these edges, this is no longer a connected graph. This is a graph with 2 connected components. So how can we tell if 2 nodes are connected? If we can even get from one node to another one, well, that's where we're going to use our breadth first search. But and you could, with this graph, you can just look at it, and you don't need to train a computer to do this. You just look at the graph and, just kind of look at it. You can look at this graph and figure it out. But the internet's a little bit bigger than it used to be. We have a lot more connections, a lot more going on. We're going to need computers to solve this. We need to automate this process so we can just hit a button and have the computer figure it out. Same with our movies.csv data. There's far too many movies for you to go through and actually manually calculate the distance between any 2 actors. You're just never going to do that. No one would ever bother. But we can train a computer to do it, which we'll do in task 8, and that is going to let us do it in like a millisecond. And we'll be able to figure out the answer between any 2 actors, what's their distance. Alright, sorry, that's bugging me. Degrees of separation. Yeah. I've said that so many times. It's so weird I blanked on that one. Alright. So we have to train the computer to find these connected components, and we're eventually going to find distance with breadth first search, but we're going to go through breadth first search 4 separate times. We're going to do 4 separate runs of breadth first search and add more and more information each time we run it. So here's the simplest one. We're just going to go over the top level what the algorithm is, and we're going to use it to find the connected component of a particular node. The connected component of a node is the connected component that contains that node and should return all of the nodes in that connected component. So what we'll do is choose a starting node, and then we're going to explore all the neighbors of that starting node. Then we're going to explore the neighbors of the starting node. Then we're going to explore the neighbors of the neighbors of the neighbors of the starting node, and we're going to keep repeating this process until no new nodes were visited in the last round. So once we didn't add, we went through a whole round of neighbors, 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 neighbors. Once we go through one of those rounds where we add another layer and didn't add any new nodes, we didn't visit any new nodes, that's when we're done and we've found the entire connected component of that node, which we can visualize here. We know that we did, in fact, do that with 2 steps because we've explored every node that we're going to explore. We can't get to this other connected component, so we know that we've explored this entire connected component. So this is the connected component for UCLA. And then if we want to find all the connected components of a graph, we'll take any node we haven't visited yet and repeat the process. And then if we still haven't visited every node, we take another node we haven't visited and just keep doing that until we've visited every single node. You have all the connected components of a graph. And when we're doing this, we'll see this when we go through the more in-depth runs of this, but we want to, what's up, Tella? Then what we want to do when we're in those more detailed runs of this is we have to make sure we're never visiting a node twice. Because once we start visiting nodes more than once, we're probably going to go infinite. And once we go infinite, of course, we're done. Everything's screwed after that. So we want to make sure we never visit a node twice. Because if we're visiting a node twice, then we're going to visit its neighbors a second time, then visit it a third time, and we're probably going to go infinite. So never visit a node twice. We're visiting every single node exactly once. And we're going to use a queue to track the order in which we visit the nodes. The order is going to be important. The order is what makes this breadth first search versus depth first search. So we're going to use a queue to track the order in which we're going to visit the nodes, or rather explore the neighbors of each node. We're going to initialize the starting node in that queue, and then whenever we find a new node, we're going to in-queue that node, and then we're going to run until the queue is empty. So there's a lot of, and I'm blowing through this slide really quick. Usually this is the end of a lecture, so I'm saying this just to set up the next lecture, but we're about to go right into the next one. So I'm not going to spend too much time on this slide. We're going to go into all the details on this right now. So this is the high level overview of how we're going to track that, because there's a lot of hand waving in the way that I just did the algorithm and just said, yeah, explore the neighbors of the neighbors. But how do we actually do that in the code? Well, the answer is use a queue. So we learned queues way back. That's going to come back in a major way. We're going to need a queue to track all of this information. Which we built a queue. You can just use the queue we built in class. You can use an array list as a queue, a linked list as a queue. You can do whatever you do to get the job done, but you need the concept of a queue, this first in, first out data structure. That's what you need. And when we did the queues lecture, I emphasized it's the concept that's important, not necessarily the data structure. But if you use the data structure too, you get all that O of 1 efficiency, which isn't the biggest deal in 116. We don't care too much about efficiency, but why not? Why not be efficient? And those details are to come right now. If you want to know if 2 nodes are connected at all, start at one of those nodes, run breadth first search to find the connected component of that node, and then check if the other node is in that connected component. If it is, those 2 nodes are connected. If not, those 2 nodes are not connected. Which in your assignment, the degrees of separation, this would be starting at one actor. If you don't even find the other actor in your run of breadth first search, you know that they're not connected at all. In their degrees of separation, I think you're supposed to return -1. I forget what I'm pretty sure it's -1, what the return value is if they're not connected at all. Okay, done with those. And just to show you the very last one, this would be our last memory diagram of the semester, but we're not going to do it because a graph is built off the adjacency list, which is a hash map of values to an array list of values. And then everything is just working with that hash map, hash maps and array lists, which hash maps and array lists we've been doing since lecture 2. We've been doing since week 1. So there's nothing new in this memory diagram. I don't have any new concepts to talk about. Like with polymorphism, I was talking about the difference between the object type and the variable type. I had some conceptual stuff to talk about. This is strictly just extra practice for memory diagrams, and it's something that I'm not even assessing you on a quiz. So no need to go through these. We're going to do live coding instead when we get to that point. Get to that part. But we will definitely go over these slides. This is the, dare I say, the most important part of this lecture. Everything we've done so far was setup. This is pathfinding with breadth first search. This is what you need to do in your task 8. Just give me 1 minute, though. I'll be right back. All right, and we back. Okay. So we defined a path. Path is a sequence of nodes where each consecutive pair of nodes is connected by an edge, but we didn't introduce the length of a path. So the length of a path is the number of edges in that path, which is equal to the number of nodes in the path minus 1. So this path, Lincoln, MIT, Utah, SDC, RAND, UCSB, SRI, is 1, 2, 3, 4, 5, 6 edges, 7 nodes. So the length of this path is 6. And then we can define distance, which we already talked about. I guess length of a path is new. Then we can talk about distance, where distance is the length of a shortest path between 2 nodes. And I say a shortest path because there might be multiple shortest paths. For example, between Carnegie and MIT, there's 1, 2, 3, 1, 2, 3, 2 paths of length 3, which is minimum. So there can be multiple shortest paths. So I had to say a shortest path, not the shortest path. But the distance is the length of a shortest path between 2 nodes. So what's the fastest we can get between 2 nodes? Lincoln and SRI has a distance of 3 because there exists a path, this path right here of length 3. And try as you might, you're never going to look at this graph and find a path of length 2 connecting those 2 nodes. And any 2 nodes that are connected by an edge, their distance is always going to be 1. So RAND and BBN has a distance 1 because they're connected by an edge. So that's distance. And distance is the key thing that we need for task 8. The degrees of separation between 2 actors. You know what? Let me just introduce task 8. I mean, that's what you're all here for anyway. Let's talk about it. So we need the degrees of separation between 2 actors in the in that movies.csv, where 2 actors are connected, and I'm going to be pretty blunt and straightforward with this one, is 2 actors are connected. We want to build a graph. It's the graphs assignment. And 2 actors are connected if they've starred in a movie together. So you're going through all of your movies and creating a graph. Every movie has a cast list. For every pair of cast members in that movie, you're going to add them as an edge, as a bidirectional edge, to your graph. That builds your graph where every 2 actors, if they start in a movie together, they have an edge between them. You've added an edge between them. That's your graph, which does take a bit. You know, I'm making it sound straightforward there, but you got to iterate over all of the movie data in, you know, fairly complicated ways. Like you're going to have a triple loop in there. You should have a triple loop in there somewhere to go through each movie. And for each movie, you want to iterate over the cast. And for each cast member, you want to iterate over all the cast members again. Not necessarily all, but that's up for you to figure out. And once you have your graph built where there's an edge between every two actors who have started a movie together, once you have that graph, the degrees of separation between two actors or two cast members is the distance between them in that graph. So when I'm asking you to compute degrees of separation, just read that as distance in the graph. If you build the graph the way I just described, distance, degrees of separation is exactly distance in that graph. So what you're asked to do for task 8 is find the distance between two nodes in a graph. That's what this assignment boils down to, by design, of course. That's what this assignment boils down to. What's the distance between two nodes in a graph? But with some flavor, so it's not just literally, here's a graph, find the distance between two nodes. So how are we going to compute the distance between two nodes in a graph? Because that's the most challenging, that's the toughest part of the assignment by design. That's what I want you to be focusing on when you're working on that. There's two halves of it. Building the graph first, I'd say that's, 25% of the assignment. And then finding the distance between two nodes, that's the other 75%. But at the same time, that 75%, I'm about to walk you through and hold your hand pretty closely on this one, if I'm being honest, of how to actually compute that, how to do that. Okay, so distance between two nodes in a graph, this is what we want to figure out. Like I talked about connected component to like build up to this, but really it's distance in the graph. The connected component stuff is really just to say, figure out how, if two nodes are not connected and you're going to return -1 in that case, how to figure out that situation, that edge case. But this is the big one we're after. Distance, that's what we want to figure out. How are we going to use breadth first search to find the distance between two nodes? And I said we'd run through breadth first search 4 times. So let's do this 2 more times. It's going to sound weird just setting this up, but the 3rd time is going to be the one that most closely follows what you'll do in the homework. The 4th one is kind of like a bonus one. In the fall and spring semesters, you know what? Let's just go through it. You'll see it when we go. But the 3rd one is the most important one. But if you don't understand the 2nd one, you're not going to understand the 3rd one. So here's the 2nd one. Let's talk about this. So let's run through breadth first search again, except when we're visiting new nodes, we're going to keep track of the edges that we've used to be able to discover new nodes. So let's start at Carnegie, because we started at UCLA last time. So today, this section of lecture is all going to start with Carnegie as the starting node. So let's start at Carnegie, and then when we explore a node, so we explored this starting node, we're going to represent that node over here in a separate data structure where we have the node Carnegie, and then whenever we explore a new node, we're going to draw in the edges that we used to discover those new nodes, and we're going to go visually lower every time we explore a new node. So then Case and Harvard are going to explore Lincoln and BBN respectively. So we'll go down and explore those new nodes. Then with Lincoln and BBN, they are both going to fight over MIT. The important thing here is that only one of them is going to explore MIT. And this decision is made arbitrarily, which is a decision you won't even have to make in your code. Well, oh my goodness, excuse me. We'll see later that this is, the decision just happens. It just happens. But for the slide, I have to make the decision. So I'm going to choose Lincoln to explore MIT. So Lincoln explores MIT. When BBN looks at MIT, it's going to see that it's already been explored. It's already been visited, so we're not going to bother going there. So this edge right here never makes it into our other graph over here because it wasn't used to discover a new node. And then MIT is going to find Utah. Rand's going to find a whole gaggle of nodes here. So we're going to draw these in, again, visually lower on the slide. And then let's wrap this thing up. We have a bunch of edges here, the edges in white. These edges were not used in our other graph over here. And what we end up with is this new graph, which is a breadth first search tree. This is actually a tree because it will not have any cycles. All of the edges that we removed, if we added any one of those edges in, it would create a cycle. So this is technically a tree, even though we're using a graph to represent it. This is, in the world of theory anyway, this is theoretically, it matches the definition of a tree. We're not representing it as a tree the way we represented trees in our code, but it is, technically speaking, a tree. It meets all the conditions of a tree, i.e. no cycles. So this is a tree, and what's more is there's levels to this. So we can label these levels the way that we had all the edges go down. We can start, if we say level 1, and each time we go down, we advance to another level. Carnegie, and then down 1, Case and Harvard are at level 1, Lincoln and BBN on level 2. Every time we travel a new edge, we advance to another level. And these level numbers are exactly the distance from the starting node to each node in the graph. So from Carnegie to UCSB, the distance between those two nodes is exactly 4 because UCSB landed on level 4. From Carnegie to SRI, you're never going to find a path shorter than 5 because SRI is on level 5. So it has distance 5 from the starting node. And notice this is only from the starting node to each node. So if we can get this information, this distance information, and we need to find the distance between two cast members in a graph, we're going to pick one of them as a starting node, run breadth first search, and figure out the distance, look up the distance of the other node that we're looking at, that we're trying to figure out. So actor A, actor B, choose one of them, actor A as the starting node, run breadth first search, and figure out what level actor B landed on. This is the nice information that we can get out of breadth first search. It's why we don't talk about depth first search in 116, because we can't get this information out of it. But breadth first search, we get this nice distance information. We get the distance from the starting node to any other node in the graph. Very useful information. So this is what we want to do, but we have one big problem. Big problem is how the hell are we going to code that? I'm talking about things like draw it visually lower on the slide and just a lot of hand wavy stuff that's like, oh, don't worry about it. Just do this. How do you code that in your assignment? It's way too abstract. I left out way too many details. I don't know how to code that. So this was our second run of breadth first search. Now is our third one. The third one, we're going to do the same thing, same concept, same idea of tracking these levels and the distance, which I'm going to drop the level thing and just call it distance from now on. But instead of just visually lower on the slide and stuff, I did this just to show you the idea of what we're headed towards. But now let's introduce some data structures and talk about how you would actually code this thing up. How do you actually code up breadth first search while tracking distance? That's what we want to do here. And let's just do that. So we're going to want 3 different data structures to do this. 3 data structures. In your code, before you run breadth first search, you should be initializing 3 data structures. And let's go through what these 3 data structures are. So 3 data structures. 3 data structures. Okay, first one, a queue. I guess there's no particular order here, but the first one that my slides are going to talk about, so the first one I'll talk about is a queue. We want to track all the nodes that need to be visited, or rather all of the nodes that we need to visit the neighbors of. So that's all going to be tracked with the queue. This is where we're going to use a queue instead of a stack. If we use a stack, we get depth first search. We use a queue, we get breadth first search. Oh, I didn't mention that earlier, did I? That was a big reveal. Anyway, if we swap this out with a stack, we get exactly depth first search, which is another algorithm that I'm not going to talk about in detail. It's not useful for our purposes. It's not going to get you degrees of separation or distance or any of that. A queue is going to give you breadth first search, which does give you that information just based on the order in which we're going to visit the nodes. A queue is going to track them in exactly the order that we want to visit them. So we're going to create a queue to track the order in which we'll visit the neighbors of each node. Some data structure, I'm going to leave it vague, but most students end up using an array list for this, which is fine. That's fine. The more proper data structure, the better data structure is a set. I like using a set, but since we haven't talked about sets in 116, I'm not just going to throw that out there for you. If you want to use an array list so we can stick to the data structures that we have talked about, an array list for this is going to be fine. But a set is the more efficient data structure for this, but array list is going to be fine for 116. We're not too concerned about efficiency. But whatever data structure you use here, I'll say array list just because I think that's what most of you will end up using, is what am I saying? A data structure to track which nodes have already been explored. So, and visually I'm going to mark them in orange. Orange means that Carnegie is in this array list that is keeping track of what's been explored. You could also use a hash map here for what it's worth. If you want to use a hash map and map that to true or false, true if it's been explored and false otherwise, however you want to represent this information is fine. Array list you can do add to say, okay, this has been explored now, I'm going to add it to my explored array list, and then dot contains, because you're going to have to look up, has this node been explored already? That's the big question we're going to have for this data structure. Set can do that very efficiently. If you use a hash set, that's going to be an O of 1 operation. That's why set's the nice one. With an array list, it's going to be an O of n operation, but I mean, we're not that concerned. In 250, you better be using the right data structures. It's literally the name of the course. 116, I ain't gonna get mad if you use an array list for this and have O of n operations. What's a hash set? A hash set, it's built like a hash table. Like we've been using hash maps all semester where we have keys mapping to values, where the hash map is, I need a succinct definition for this because it's like a week or two of 250 content to talk about hashing. But I want to give you a brief answer. Is a hash map that we've been using all semester is a hash table based on the keys of that hash map. A hash set is basically a hash map but without the values. It's just tracking the keys. So what a hash set will do for you is give you O of 1 lookup, which a hash map does too. We have never talked about efficiency of a hash map, but it gives you O of 1 efficiency of looking up the value at a key or if it contains a key. Hash set does the same thing, just doesn't have values. It just has the keys effectively. And it will not allow duplicates. So if you've taken 191, you've talked about the concept of a set where you can't have duplicates in it. A set in our code is going to be the same thing. It's a data structure that doesn't allow duplicates. So if you add a value into your hash set multiple times, it's only going to appear in that data structure one time. So if you just overload it with a bunch of data, it's going to remove all the duplicates for you. And the way it does that, the very brief explanation of how it does that, if you want to check if it contains a value, for example, it's going to take a hash of that value. It's going to apply a hash function to that value and then look up in an array at the index of that hash value and look for the value that you have there. And if you insert into it, it's going to take the hash of what you insert, and in an array, it's going to go to that index and insert at that index. So one application of the hash function, and then it's a random access lookup. So it's a very efficient way to find if the value is in that data structure, very efficient way to add and remove from the data structure. But it doesn't have any concept of order. The order is in the order of the hash values of your values, the hash function outputs of your values, which is why a hash map, we get that random ordering. It's because it's ordered by the hash values of the keys, and that hash function isn't necessarily something we're privy to. Like, we don't I don't care what the hash function is that's being used. In 250 you will, because you're learning how the data structure works. But when I have a hash map where the keys are strings, I'm using the hash function for strings, which is somewhere in the Java code. It's the in the string class, the hash code method, which I don't know what it is off the top of my head, but it's using that and then ordering by that. So that's my brief explanation of it, which wasn't that brief, but yeah. So if you use a hash set here, you're getting that nice O of 1 lookup because you're checking does this hash value exist in this hash table. With an array list, you just have to go index by index. Hey, index 0, do you have this value? Index 1, do you have this value? Index 2, do you have this value? It's a much slower operation instead of jumping right to, because if that value is in your hash set, it has to be in the bucket for that index of that hash of that value. If it's not there, it's nowhere. So you can just safely say, oh, it's not there. It's definitely not in this thing. Okay, back on track though. So we have this array list or hash set of values, which is going to track what's been explored already, or hash map. Honestly, you can use so many different data structures for this. But array, if you don't want to think about it, array list. If you do want to think about it, check out a hash set. It's nice. It's easy to use. You're only using add and contains. It behaves exactly the same way as an array list for this use case, since those are the only two methods that you're going to call anyway. You just create a hash set instead of an array list. So that's how we're marking these as explored. If it's in this data structure, we're going to mark it as explored just by putting it in that data structure and then checking if it contains it. And it's going to be important to avoid our infinite loops. So orange means that Carnegie is in this data structure that's tracking my nodes that have been explored so far. And then finally, the hash map or a map, just any map, but hash map's the one we've been using, is going to track the distances of every node. So we're going to track for every single node in the graph, what's the distance from the starting node to that node. And for the slides, just for the slides, I'm initializing all these values to infinity. You wouldn't have to do this in your code, and I wouldn't even recommend it. I don't do it in my solutions. But this just makes the slides more, makes it so we're not changing the structure of the slides every time I click. It's just something that bugs me. In reality, you would have this hash map, which would just have one key value pair at this point, Carnegie to 0, and all of these other keys would not yet exist in the hash map. They won't exist until we explore those nodes. Then we're going to add those key value pairs into the hash map. But this is going to track the distance of every node. My infinity symbol just means we haven't explored that node yet. And there might be some nodes that we don't explore if they're not in the connected component of the starting node. We'll never get there. We'll never explore them. If we initialize the hash set, is it to type movie or type string? String, right? Because the title is a node. Yeah, string. So and I'll just give this one away. It's you want a graph of strings, and then just do the titles of or not the titles, because your nodes are actors, not movies anyway, and your actors are strings. The name of the actor is a string, so you want a graph of strings. Yeah, our nodes aren't movies. They're cast members of movies. So definitely strings. And then once we have our 3 data structures, we want to initialize them all. I kind of skipped this when I was talking about them because I want to talk about it now. We want to initialize them all with the starting node. So we create our queue and we enqueue the starting node. We create our, no problem line. We create our, now we talked about hash sets, our array list / hash set. We talked about hash sets, so I want to call this hash set now. It is the more fun way to represent this and more efficient. So whatever data structure you're using to track the nodes that have been visited, mark your starting node as having been visited. And then in your distance hash map, mark your starting node as distance 0. From the starting node to the starting node, you don't have to traverse any edges. Distance 0. A node's distance to itself is always 0. So from the starting node to the starting node, distance 0 of the starting node. And then we're ready to run breadth first search. So this is all the setup. Before you get into breadth first search, your degrees of separation, first thing, either create the graph. Some people create the graph in their degrees of separation method. You can do that. That's fine. It's wasteful, but it's fine. Or preferably create the graph in your degrees of separation constructor. Create the graph once, and then you can call degrees of separation 100 times if you want, without having to recreate the graph every single time. But if assuming the graph's already created, the first things you do in your degrees of separation, create these 3 data structures, initialize your starting node, and then you're ready to go. Then you're ready to jump into breadth first search itself. So with breadth first search, and my commentary goes away here, it's all going to be audible. I'm just going to explain as we're going through each slide. We're going to run breadth first search until the queue is empty, which sounds like we're doing something while some condition is true. Not to just give it away and write your code for you, but you're going to want to do this while the queue is not empty. So whatever data structure you're using for the queue, if you're using the queue that we built in class, it doesn't have an isEmpty method or a size method because they're not in queue or dequeue. Those are the only 2 things you need for a queue. So you'll want to add some way to check if the queue is empty if you're using that queue. So while the queue is not empty, this is what we'll do. This will be on the very first step. It's going to be everything for depth first search. We will go through the entire graph. So it'll get kind of repetitive here, but just to make sure we get all the points out there, everything that you need to know. But we're going to do this while the queue is not empty. We are going to dequeue. So we're going to dequeue Carnegie. Actually, let me park on this slide a little longer. We're going to dequeue Carnegie, and we're going to check all of the neighbors of that node, of Carnegie in this case. We're going to check all of the neighbors, and for each check, we're going to go to our adjacency list, give me all the neighbors of this node, and for each of the neighbors, we're going to check. We're going to look at this data structure and say, have I explored this node before? So we're going to visit case in Harvard here. When we get to case, we're going to ask ourselves, have I explored this node before? The answer in this case, for case, is going to be no. So if we have not explored the node before, we're going to do 3 things, and they relate exactly to our 3 data structures. We're going to mark it as explored. We're going to enqueue it into our queue, and we're going to update its distance, or not update, I shouldn't say update. We're going to mark its distance. We're never updating distances. You're never changing any numbers. Once you add a distance, it's solid. That's why you can't say update here. We're going to mark its distance as the distance of the node that discovered it plus 1. So Carnegie's distance was 0. We're going to add 1 to that. Case's distance is 1. So we didn't explore the node yet. So we're going to mark it as explored, enqueue it, set its distance to the distance of the node that discovered it plus 1. And then same with Harvard. We're going to look at Harvard, haven't explored it, mark it as explored, enqueue it, set its distance equal to the distance of the node that discovered it plus 1. And that is the entire algorithm. We just repeat that. At that point, we're at the top of the while loop again, and we just let her rip. Dequeue, check the neighbors, update our 3 data structures. May have missed this, but what do you mean by queue made in class? Is that I should have a queue class made in my ratings package? Like we had a lecture in the linked list lecture is the last part of that lecture. I made a queue, like in class, I made a queue class. Spent like half an hour on it. Talking about the queue class and the enqueue and dequeue methods. It's in the repo. That's what I mean is that queue class that we created in lecture. It wasn't on any assignments yet, so if you're, well, that's, but it was a while ago. So, but it's in the repo. You can use that one, or you can use an array list and just use it as a queue. Look up the syntax of how to remove the first node or node by index of an array list, or use a linked list. Yeah. Oh, yeah. Okay. Cool. Yeah, we got there. But if you do use the one from lecture, you do want to add some way to check if it's empty, because you have to go, well, it's not empty. And honestly, what I would do is add a getter for either the front or back and check if it's null. Once front or back are null, if one of them's null, they should both be null. That's when your queue's empty, and you're done. Other than that, enqueue and dequeue are the only other two things you need, and you already have those. So I would use that class. I think that's the easiest way to get task 8 done for the queue portion. And you can take that class, copy and paste it into your data structures directory, that package in your project, and then just use that class. It's the easiest way to do it. If not, you can build your own queue. You can, you have other options, but I think that's the easiest one. Okay, then we repeat the process. We're just going to do this until the queue's empty. So case, we're going to dequeue, and we're going to check its neighbors. We're going to look at Lincoln. We see that it's not been explored yet, so we're going to explore it. That means we mark it as explored, so we're going to add it to our array list, hash set, whatever data structure we're using here, hash map even. We're going to mark it as explored. We're going to enqueue it, and we're going to set its distance equal to the distance of the node that discovered it plus 1. Case's distance is 1. Lincoln's distance is going to be 2. And then we're going to check, because we're going to the array list and getting all of the neighbors. We're going to get every neighbor every single time. And here's one of the important parts. As long as you're doing this right, it'll just happen automatically. But this is where this data structure is going to come in crucially. Is Case is also going to check Carnegie. And if we end up exploring Carnegie and enqueuing it, we're going to go infinite. Because then when we get to Carnegie, Case and Harvard are getting queued up. Case and Harvard are going to queue up Carnegie. We're going to get an infinite queue. You're going to get, what do you get? It'll just won't run. Well, you'll run your code and just, it'll look like nothing will happen. But it's because your queue is just constantly running and running and running and constantly visiting nodes that you've already visited, because you're stuck just bouncing between Case and Carnegie and Harvard and never really making any progress. So if you do that, you'll run your code, like you'll run your tests, and it'll be thinking and thinking and thinking. You won't get any Stack Overflows because we're not using recursion. Nothing's going to blow up. Nothing's going to break. It's just going to run forever and never finish. So if you see that, double check this data structure. Make sure you're never exploring a node that's been explored. So Case is going to look at Carnegie. It's going to peek at Carnegie and say, have I explored this node already? And this time the answer is going to be yes. Yeah, we explored that node already. So we don't do anything. There's nothing to do. If you've already explored a node, you don't do anything. You just skip it. So in that while loop, we're dequeuing. We're getting the neighbors of that node. So we're in another loop where we're checking the neighbors of this node. And we have a conditional. If I've never visited this node before, do a whole bunch of stuff, update these 3 data structures, else, nothing. There shouldn't even be an else block. You're not doing anything. You're just getting to the end of that loop and going right to the next neighbor. So we don't want to do anything if we've explored the node. Because once we add a node to this, like once we add Lincoln to this data structure, Lincoln's distance is 2. Like, we can verify that visually. This distance is 2. But that's what breadth first search is going to guarantee, is once we add a node to this data structure, we are adding its actual distance. That is a shortest path. In this case, is the shortest path from Carnegie to Lincoln. This is the shortest path. And breadth first search will always find a shortest path from the starting node to every single node. That's what breadth first search does for us. Because we're visiting the nodes using a queue, we're going to get them in exactly distance order. And that's always going to give us the distance. When we explore a node, it is via a shortest path. Yeah, you can use the graph class from lecture. I would just cut and paste that into the data structures package and just use it straight up. Yeah, the one in the repo. The one in the repo and the one in class is the same. Well, the one in the slides is just trimmed down a little bit to fit on the slide. I would grab the one from the repo though, and then remove anything that you don't need, or leave it in there. Who cares if you have extra stuff in there? I might remove the add edge method just so you don't accidentally call it. I've seen students accidentally use add edge instead of add bidirectional edge. You don't want to use add edge unless you're sure that you're calling it twice in both directions. But it's easier to just call add bidirectional edge. Okay, and then we repeat. We DQ Harvard. This is pretty much the same thing. It mirrors what we did with case. When we check BBN, we mark it as explored, in-queue it, and set its distance to Harvard's distance plus 1, so 2. And then we check Carnegie. Carnegie's already been explored, so we don't do anything with Carnegie. We already have its distance. We don't want to get in a situation where we're in-queuing Carnegie, that goes infinite. We also don't want to put Carnegie's distance into this graph. We don't want to update this distance to 2, Harvard's distance plus 1, because we know Carnegie's distance is 0. We know that, 1, because it's already in the hash map, and 2, because it's the starting node. It better have distance 0. If it doesn't end up with distance 0, we're in trouble. So if we ever update a distance in this graph, we're not actually getting the distance. We're getting just some number that's not representing the distance. Okay, then we DQ Lincoln. And this is where we're going to see that tie between Lincoln and BBN. One of them is going to discover MIT and the other one isn't. Which one? Well, it's whatever one was in the queue first. Lincoln is going to explore MIT. So we DQ Lincoln, check MIT, mark it as visited, in-queue it, and set its distance to 3, which is Lincoln's distance plus 1. Lincoln checks case. Case has already been explored. Don't do anything with case. And then when BBN checks MIT, it's already going to be explored. So BBN says, MIT has already been explored. I'm not going to do anything. Harvard's been explored, not do anything. Rand, I'm going to explore, in queue, and set its distance equal to 3. So Lincoln got MIT, but there was nothing we had to code. There's no extra logic that says how we're going to break the ties. It all just comes out in the wash. It just happens. And the way the tie was actually broken depended on the adjacency list. So the way that I set up this example, I'm just saying that Carnegie's adjacency list is case and then Harvard, as opposed to Harvard and then case. So that means we visited case first and in-queued case first and then Harvard, which meant case was DQ'd first, which means Lincoln was in-queued before BBN, and then Lincoln was DQ'd first, and Lincoln got MIT before BBN could get a chance. So what it actually depended on, where the tie was actually broken, was when we created the graph, and if we added this edge Carnegie case before we added the edge Carnegie Harvard. Which either way, it doesn't matter. If BBN found MIT, BBN's distance is 2, MIT's distance would be 2 plus 1 is 3. Well, it was still 3. Because these are both distance 3, these are both length 3, MIT's distance is going to be 3 no matter which one of those paths was used. So whenever there's an arbitrary decision like this, where 2 nodes could possibly fight over a node to see which one discovers it, whenever that's the situation, whenever that's the case, that means that we have multiple shortest paths and it really doesn't matter which one we use. Either way, the distance will still be the same. It will not change our answer in terms of, at least in terms of task 8 and distance, degrees of separation. It will not change our answer, so it does not matter. It's an arbitrary decision, which a decision we don't even have to make. It'll be dependent on the how you iterate over your movies. It'll really end up depending on the order of the cast lists in the movies.csv file. It's such an arbitrary decision, and it doesn't matter. Not something you need to worry about. Because I'll have students ask, how do you code up how this decision is broken? The answer is you just don't. It just happens. It just kind of happens. Not something you have to worry about at all. And no, I want to go a few more steps first. So MIT, DQ MIT, we're going to check Utah, mark it as explored because it has not been explored, enqueue it, set its distance equal to 4, MIT's distance plus 1, and then RAND, just to be thorough, and MIT is going to check Lincoln, already explored, do nothing, BBN, already explored, do nothing. Then we have RAND, we're going to DQ, we're going to explore 3 new nodes, we're going to mark all 3 as explored, we're going to enqueue all 3, and then we're going to check BBN, see that it's already been explored, and don't do anything there. So we get 3 new nodes, a big 3 nodes, all explored, all with distance 4, because RAND's distance was 3. And notice what the queue is doing for us. What the queue is doing is exactly visiting the nodes in distance order. So we first enqueued the only node with distance 0. So we got 0, the only node with distance 0 enqueued first. And then we enqueued all of the nodes of distance 1. All of the nodes of distance 1 are exactly the neighbors of the starting node. We don't need any algorithm to really analyze that. We're iterating over all of its neighbors and enqueuing them all. The only way to have distance 1 from the starting node is to be a neighbor of the starting node. So we enqueue all of the nodes with distance 1. And then as we're visiting them, when we enqueue nodes, we're enqueuing all the nodes of distance 2. But the first node of distance 2 that's enqueued is going to be after all of the nodes of distance 1. And we just visited all of the nodes of distance 3. We DQ'd MIT and RAND, the 2 nodes with distance 3. And then we enqueued all of the nodes of distance 4. That's what we have right here. All of the nodes of distance 4 enqueued. And we've enqueued all of them before we enqueue any node of distance 5. So next we're going to DQ Utah and get SRI with distance 5. And since we've enqueued a node of distance 5, we know that we're done exploring nodes of distance 4. So the queue is getting us exactly distance order. And since we're always DQing the lowest distance node that we haven't explored the neighbors of, we're always going to find nodes in distance order. So right here we have all the nodes of distance 4 to DQ. We've already DQ'd all the nodes of distance 0, 1, 2, and 3. So if we haven't explored a node yet, we know that it has distance greater than 4. Because if it had distance 4 or less, if it had distance 4, we would have found it when we were exploring all of the nodes of distance 3. We had to have. Because what we're doing here is saying, okay, UCLA, your distance is 4, and we're just taking that as fact. We're saying, UCLA, your distance 4, because that's what breadth first search said. You are distance 4. And we've already explored all the nodes of distance 3 or less. So if UCLA is finding a new node, it's going to find Stanford here. Once it finds Stanford, we know that there is a path, that the shortest path between Carnegie and UCLA is distance 4. It's this path right here that we found. We know the distance from Carnegie to UCLA is 4. And if we can get to Stanford with one more node, and we know that Stanford's distance isn't 4 or less, or one more edge, then we know that whatever path we use to find UCLA with distance 4, it takes one more edge to get to Stanford. So Stanford's distance must be 5 because I'm going to use whatever this path was of distance 4 and then take that one extra edge to get distance 5 for Stanford. So that's why we're always adding 1. We're saying, okay, MIT is distance 2. I don't remember what the path is. It's whatever. But I know I can get from the starting node to MIT in 2 nodes, a minimum of 2 nodes. And then I discovered Utah by following one more edge. So I must be able to get from Carnegie to Utah in 3 nodes, in 3 edges, because I'm going to take whatever path I used to find MIT in 2, and then this edge here to get to Utah in 3. So that's what we're doing when we're updating these distances, is we're finding an edge and then updating, okay, this distance plus 1 because I have one extra edge. And then UCLA is going to check these 3 nodes. They've all been explored, so we don't do anything. And at this point, the algorithm's effectively done. But if we're just going, well, there's something left in the queue, keep going, our code is still going to keep running in circles. It's spinning its wheels a little bit here, which is perfectly fine. UCSB is going to check all of its neighbors. They've all been explored, so don't do anything. SDC, all of its neighbors have been explored, don't do anything. SRI, check all of its neighbors. They've all been explored, don't do anything. Stanford, all of its neighbors, it's been explored, don't do anything. And now the queue is empty. So our while loop is finally going to break. And now we have all of the information that we could possibly want, that we could possibly extract from BFS. We have all of the distances from the starting node to any other node in the graph. So we have all the distances, the same distances that we saw on the slide with the levels, except now we have these 3 data structures. We have a good idea of how to actually code this up for task 8. We can actually extract this information in our code. And we have all the distances from the starting node to any node, at least in the connected component of Carnegie. So if you have 2 disjoint movies or sets of actors where none of these actors have been in any movies with any of these actors, you might have never explored the ending node that you're looking for, but we will get all of the nodes that we can reach, all of the nodes in that connected component. So there's a few edge cases for your homework. If you've never explored the other actor, then you know you're returning -1. They are not connected. Just return the -1 to indicate that. Sometimes one or both of the actors aren't even in the graph. It's one of our edge cases. But if they're both in the graph and in the same connected component, one of them as a starting node, run breadth first search, and then look up your ending node. Say you want the distance from Carnegie to Utah. You're going to start at Carnegie or Utah. You could do it the other way around. Start at Carnegie, run breadth first search, get the information of the distance from the starting node to any node in the graph, and then in your hash map, look up Utah and return whatever value you have for Utah. And that's finding distance from breadth first search. Let you think about that a sec. Just one last break. I had to feed my dog, let him out, and now I gotta let him back in. I can hear him crying again. I'll be right back. All right. So that's everything you need for task 8. Is you create your graph of actors based on your movies.csv data. You have 2 actors. Your degrees of separation is going to take 2 strings, your actors, and you want the distance between them. Choose one of them as the starting node. run breadth first search using your 3 data structures, and then look up the ending node in this hash map. Whatever value it has, that's your answer. That's your degrees of separation. That's your distance between the 2 nodes. That's your degrees of separation between those 2 actors. So that's your task 8. If there are any questions on that, I guess if there were questions, you would have typed them while I stepped away for a second. So let's go on to the next thing. This in the fall and spring, we started having students do this again, which I think is super fun. This summer, again, it's too fast. I feel like y'all are overwhelmed anyway. Just looking at the submission rates for the expected deadlines, I feel like you're all just exhausted right now. I feel you too. I'm ready for summer proper to start, which is pretty damn soon. So there would be no way to really fit this in the summer. It'd be ridiculous. It'd be just torture at that point. But it is super cool, so I am happy we get it in the fall and spring, and I still want to explain how this works, is how we would do pathfinding with breadth first search. So this is cool that we got the distances between each node, but what if we actually want to find the paths from the starting node, the shortest paths, or a shortest path from the starting node to each node in the graph? And in the fall and spring semesters, we have a game that they build, and this is how they have pathfinding for the enemy AI. So the enemy will actually hunt down the player while avoiding walls. So we have a grid-based top-down game, and the enemies could navigate an entire maze to be able to find the player by building our graphs properly and then building these paths that go from the enemy to the player using a shortest path that avoids all walls. So it's pretty cool stuff that we get to do. We have smart enemies that don't get stuck on walls. Like if you just go directly towards the player, they'll get stuck in a corner, and they're not very compelling enemies to face. But once they start understanding that and taking, if they're like stuck in a wall and the player's on the other side of the wall, they'll actually go around it and then find the player that way. It's cool stuff. It's fun stuff. So I want to at least explain how we do that, the technology, the algorithm that we use, which is breadth first search still. But instead of tracking the distance of each node, instead we can do one small tweak here to get this pathfinding information. Instead of tracking the distance numbers, we're going to track which node discovered that node. And we're going to have some special marker for the starting node to say this is the start node. I'm the beginning node of the whole thing. And then for every other node, we're going to track which node was used to discover that node. It's just a class we use alongside readmovie, right, in testing. In testing, since degrees of separation takes an array list of movies, technically you don't need to use readmovie. So if you don't want to mess around with test files again, you can manually create an array list of movies to feed into degrees of separation, or you can use your test files in readmovie and do it that way as well. So you have a little bit of flexibility in testing this one. Yeah, I did, because I did say read the movies that I kept saying movies.csv in lecture. I'm thinking more of the application, not for testing. Like if you actually want to find the degrees of separation between 2 actors, you're not going to manually create your array list. You're going to read the movies.csv data, which is going to give you an array list, and then feed that array list into degrees of separation. Because you're never going to hard code all that into an array list. But for your testing, where you want smaller test cases, it makes more sense to manually create your array list of data. So in lecture, I was thinking of the actual application, not the testing, not how to test your methods. So sorry for the confusion there. Yeah, so you can use a file name. You can still do that, but all that would be in your testing. You would call read movie in your tests. Uh, okay, so now each time we explore a node, I'm not going to go through the whole thing and explain everything again, but this is the one change. Each node is going to remember the node that discovered it. So Harvard was discovered by Carnegie. BBN was discovered by Harvard. So BBN was discovered by Harvard. MIT was discovered by Lincoln. RAND was discovered by BBN, etc., etc. So every single node is going to remember the node that was used to discover it, not its distance anymore. So one small change to our algorithm. Everything else is the same. We'd still use a queue. We still visited the nodes in the exact same order. We used all the same exact edges. We just changed what we store in this hash map, storing the node that discovered it instead of just the distance number. And then to find a shortest path, what we're going to do is build our path backwards. We're going to start at the ending node. So we want the shortest path from Carnegie to Stanford, or a shortest path. I think that's unique. I think there's only a shortest path from Carnegie to Stanford. I think this is the only one of distance 5. So we're going to start at the ending node. That's the last node on our path. We know that. Stanford's the last node in our path because that's our destination. That's where we want to go. It would be like the location of the player. And then we're going to ask that node, who discovered you? And we're going to build our path backwards. So Stanford was discovered by UCLA. So UCLA is the second to last node. We're going to ask UCLA, who discovered you? It's going to say RAND. Well, that's our next node. RAND, who discovered you? BBN. BBN, who discovered you? Harvard. Harvard, who discovered you? Carnegie. Carnegie, who discovered you? Carnegie says, I'm the starting node. I am the beginning. I am the alpha. I am the start of everything. So once we see this, whatever special marker we use to indicate the starting node, usually null, is where we stop. And now we have our path. From Carnegie to Stanford, we have our shortest path by tracking just a small amount of information. Each node remembers where it came from, and then we build the path backwards. And when this is a linked list, we're prepending. We prepend each node. Very efficient operations. Very clean way to get this path. And then we do pathfinding. And I'm just remembering that I updated the slides for the project, the new project. So you will get a little taste of it, but I'll still explain the movies, the movie graph stuff. I kind of explained it already, but I want to revisit it now that we have the full context of what's going on. So pathfinding, this is the game that we build with revolutionary graphics. Actually, I ain't even mad at the graphics. It's pixel graphics. It's nice. I think it looks nice, but I'm from that era, so. So we want to take this level, and the goal is to have these enemies hunt down this player. Like this enemy here, we don't want them to go just straight towards the player because they're going to get stuck on this wall and just not do anything useful. So we want this enemy to be able to go around and find the shortest path to the player. So that's our goal. And what do? Well, we're going to take our level, and first we're going to represent that level as a graph. And the enemies can't go on these static, these objects here, but they can go on these. So I'm going to place my nodes on any tile where the enemy is allowed to travel. So all the values, all the nodes where they're allowed to go. So I'm creating a graph out of my level, marking my starting node and my ending node, and then running breadth first search on it. Where each node, and the edge, I didn't explain the edges, and the edges are any valid moves that the enemy can take. So I'm saying that the enemy can't go diagonally, but they can go left, down, up, right. So I'm going to connect any two nodes that are a valid move for that enemy to travel. And when we're playing the game, we're just going to see this. But the enemy AI, they're going to see this. They see a graph, and they see their ending node, they see their location, and that's it. They don't see any of the visuals or anything. And then they're going to run breadth first search, do the pathfinding, build their path in reverse, and all that stuff we just talked about, and find this A path. There's lots of shortest paths that they could go right first, they could go down first, they could go down twice. Same thing over here. There's a lot of different shortest paths here. But they found a shortest path and travel this path. They're going to store this in their memory, and that's the path that they're going to travel to get to the player. And travel along that path. They're avoiding walls. They're doing everything they're supposed to be doing by using graphs and breadth first search to do pathfinding. That's all we need to do pathfinding is graphs and breadth first search, which has its limitations. One thing you'll learn in, I think they put this in 250 now. It used to be in, you used to have to wait till 331, but breadth first search is only finding the shortest path in terms of number of edges. Once you have what we call weighted graphs, where each edge has a numeric weight, and you want to find the path with the minimum total weight of all the edges. That takes more work. That takes a more advanced algorithm called Dijkstra's algorithm. But if you only want to minimize the number of edges, breadth first search is your go-to. We are done with slides. Actually, I'm going to do some slides in the 11 a.m. So I'm not done with slides, but you're done with slides. All right, and let's do some live coding. We'll go till 10:30 with some live coding. Since I want to do... Oh, wow. When did I do that? 4/11/2025. I did that. Oh, I did that as a lecture example. I forgot I did this. This is actually what I was about to do. I was thinking this morning. I'm like, yeah, you know what? I'm just gonna go for it. Looks like I already did it, and it's already available to you. So I lied a little bit. The generating the graph is not 25% of your assignment. It's 0% of the assignment because here it is. There it is. But let's code this live because I want you to see how it's done, but I'm definitely committed because it's already there. Movie graph. Let's talk about how to generate that graph. And I did do it. You know what? I don't want to cheat. Just so you get a better live experience. So let's talk about how to generate that graph. How to take this movie.csv data and turn it into a graph. So what I want is a graph of strings. Which I'll call graph equals new graph. Week 12 graph. So I have our graph class, which a lot of this we don't need. Most incoming connections, we wouldn't need that. Valid path, we wouldn't need that. Are connected, we don't need that. We definitely need get adjacency list. Add node we need, add because it's called by add bidirectional edge. Add bidirectional edge we definitely need. And add edge we don't need. And oh my. And all these examples, we don't need any of this stuff. Oops. Missed. And the two-string, I mean, you can leave the two-string. But for your assignment, this is all you're going to need. This is the minimum that you'll need to do the assignment. And you know what? Let me leave the class like this just to make that point. Like, there shouldn't be any errors here. But let's do this live. So, yeah, anything in the repo is always fair game. So this movie graph, yeah, you can use. I did forget I did that. But it is literally what I was about to do anyway, so it doesn't change anything. But movie graph is in the repo. You can grab it. It's fair game. Because the point of the assignment is to run breadth first search. Like that's what I want you to focus on. Actually, I don't want this to be a new graph. That's what I want you to focus on. I want this to be public graph of string generate graph. And what I want to do is take an array list of movies, and create a graph. I'm going to stub it out for now just so I can get rid of all the errors in my code. Create class movie. Oh, yeah. I definitely don't have a movie. Did I create a... I just made it an array list of strings here. Let's create a movie class. Movie. I'm going to do this from memory. I don't know if it's going to be exactly 100% what the... You know what? Why don't I just make it 100%? Let's go to the movie definition. Create a class called movie constructor that takes a string and an array list of strings. String title, array list of string cast. Private string title, private array list of string cast. This dot cast equals cast. This dot title equals title. I'm not going to set up inheritance. We're just going to code everything here. And public get title, return this dot title. It says return type string, public array list of string. I'm not going to build the rest of the class. We're just going to do the getters. Get cast. That is what I was about to type. Return this dot cast. Dot, not comma, and semicolon. Okay. I want this to be static. It won't be static in your code. Do I want this to be static? Yeah, it's fine being static. It won't be static in your code. It's only static for the lecture example, so that's one thing you will have to change. Did I make it static over here? Yeah, I did. So that's one thing you'd have to change, but that's something you got to know at this point, the difference between static and non-static. So I'm going to make you do at least a little bit of work. And I want a second method, public array list of movie I guess this is read movies. Did I didn't go from a file, did I? Oh shit, yeah, I did. There's some task 6 solutions right in the repo too. Blast my memory. File name. Okay. Array list of movies equals new array list. return array list. All right, return array list. Movies. And I want to generate graph of, then make it static. Generate graph of read movies. File name, string, file name equals data slash, I'm going to use the full thing. I'm not writing test cases here, I'm just writing a main method, so I'm just going to use the full, I'm not going to mess around with my testing files or anything, I'm using the full movies.csv. And let's just print nothing to the screen so I can set a breakpoint here and we can see our graph in the end. Okay. And graph of string graph equals new graph. That much we know. Return graph. Okay, so here's our setup. This is what we want to do. So I had to just crank out a lot of code there to get the setup. But what we're doing is taking a movies.csv file. This can be a test file or what I'm using here, the full file, but something in the format of movies.csv. Calling read movies. This is going to be the task 6 method. Those of you who haven't finished task 6, first of all, get on that. That final deadline's almost here. But this will be essentially read movies unless I forget some nuances to the spec off of memory here, but it's going to be reading the movies from this file name. And then generate graph. This is task 8. This is me giving you some solution for task 8 to give you a good head start on that. So you're not hung up on how to create the graph. I do want you to focus on taking the breadth first search part of lecture and coding that up, turning that into code. Remake movie graph into this? I don't even know what that means. Remake movie graph into this. I don't know how to interpret that. Yeah, if you reword that, if you help me out a little, I'll give you, I can answer that. And then taking that array list of movies and turning it into a graph, which is one of the big things that you have to do in task 8. So that's what we want to do. Let's start with reading this movies.csv. So we're going to do this files.readAllLines of paths.get of file name. And I'm going to throw this right in a loop. In lecture, you know, I tried to keep it as little confused. Oh my goodness. I tried to minimize the confusion, so we stuffed it in an array list and did all that stuff. I'm going to be a little fancier now since it's the last lecture. You're ready for a little fancier stuff. Is I'm going to iterate over the lines directly. Oops. String line. Like I can just do this, and then I don't have to worry about what data structure that is. I don't have to worry about this read all lines returning a list, something that implements the list interface or whatever. I just don't have to care. I'm just going to iterate over whatever it gives me. I need my try catch. So I'm going to try catch IO exception. So when I don't use autocomplete, I don't get the auto import. Is the one I always regret not actually typing out the whole thing. And I actually don't need anything in the catch block. The way I'm setting this up, I'm initializing movies to an empty array list, and I'm going to try to populate it. But if I can't, I just want this to fall through to return movies, which will be an empty array list at that point. So the lines in the movie as the title, string title equals line splits of 0, which apparently I'm committed to using a plain array. I might not do that. No, yeah. Let me use an array list on this one. Array list of string because I want to remove the first value. I don't think I can do that easily in an array. Splits equals dot get. Why is that like that? Oh, because I just didn't finish the line before it. New array list arrays dot as list line. Oh, come on. Line dot split on comma. Okay, so the title, and then splits dot remove. I want to remove the value at index 0 because I already handled the title, and then array list of string cast equals splits. Movie equals new movie, and I'm not worrying about ratings. I'm not going to add all the ratings to this, so I don't have to worry about have I seen this movie before or have I not. I'm just getting the title and cast out of this. If I've seen it twice, so what? I'm going to add that should be the same title and cast both times, so I'll just replace it. That's fine. Actually, I would have duplicates. That's a bad example, but I'm just not going to have duplicates. I just know there's no duplicates in the data, I guess. But if we were adding the ratings, if we were doing the read movie ratings as well, I'd worry about more stuff like that, but I'm not worried about it. And I get some warnings because there's special methods to get first and remove first. I could be calling those, but I'd rather look at the indices explicitly. Cast, I don't know why it, oh yeah, that is redundant. So I could just do splits right here. It's saying I can remove this line. So I can condense my code a little more. I think it's condensed enough. I think that's fine. So there's read movies. And now we're going to generate the graph. We can verify, actually. Let's run the debugger and verify that we did get. That's not right. That we did get the movies that we expect. So we got 4,575 movies. At index 0, we have Toy Story with Tom Hanks, Tim Allen. Looks good to me. We can double check to make sure that Tom Hanks is the first cast member. So movies.csv. Tom Hanks is the first one, just to make sure we didn't lose a cast member. And we want to make sure Toy Story isn't the first cast member. So we did properly remove just index 0, and then the rest was the cast list. And we can go to the end, Penn Jillette. So we do have the full cast list. That's not proper testing, but it is a sanity check. It gives us an idea that we're on the right track. But we don't have, actually we kind of do have some time to do a full example. We don't not have time. But I'm not going to do full testing for this one. Okay, so to generate the graph, we created the graph, and what we want to do is call add bidirectional edge a whole mess of times. So we're going to need some loops here. We're going to iterate over the movies. Movie, and movies. So for each movie, I want to iterate over the cast members. Actually, I'm going to do this wrong first because I see this a lot, which in the end, it doesn't matter. I'll explain as I go. But I am going to show this a bad way first. Is let's iterate over, which a lot of you might do, unless you're just taking my code. Nobody should be doing this because you should just take my code in this case. But for string cast member in movie.getCast. So I'm going to iterate over all the cast members. And then I'm going to iterate over all the cast members, right? This is a reasonable thing to do. cast member 2, because we love numbers and variable names, right? Get cast graph.add bidirectional edge cast member 2. So if I just leave you to your own volition, this is a lot of the code that I'll see. Generating graphs will look like this. So let's set our breakpoint. So for each movie, I want to iterate over every pair of cast members and then add those edges. So if I look at my graph, except I'm using the full movies.csv, let's use a smaller one just to make this point. Those movies don't have anything in common. Yeah, let's just create a I'm going to create a test file, but not a test case. I'm not going to do testing, full testing here. I got to leave something for y'all to figure out. And let's go Jeff Goldblum. Let's find 2 movies with Jeff Goldblum. Here's one. Here's 2. Oh, no, I don't want to rant about that one again. The copying an empty string shouldn't... I obviously didn't want the empty string in my clipboard. So we already got past task 6, but this is what I was recommending for task 6. Take your cast list and just start removing cast members. We want to make sure we keep Jeff Goldblum here. Okay, that's fine. And then we want movie test 1. So we know what we expect from this, because there's such a little amount of data that we know what we should have. So we have an adjacency list of size 5. That's good because we have 5 actors here. And let's check Jeff Goldblum. He's the one we're really after. Jeff Goldblum starred with all other actors. So there should be 4 neighbors to Jeff Goldblum, all 4 other actors. But that's not what we're going to get. So we're going to get Jeff Goldblum with an edge between Jeff Goldblum 4 times, with Robin Williams twice, Brandon Smith twice. We have a lot of duplicate edges here. Now, this is actually going to work for us for our specific application, as long as all of the necessary edges are there and nothing is completely false. I mean, I guess there is no edge from Goldblum to Goldblum, but everything else is just duplicated data, which is fine for our case, because if we're visiting the neighbors of Jeff Goldblum, we're going to go Sean Patrick Flannery, visit that node, mark it as visited, okay, cool, and do all of our other stuff. Lance Henriksen, we're going to visit that node, mark it as visited. Then we're going to get to Sean Patrick Flannery, we're going to check it and see that it's already been visited and just not visited again. So our breadth first search algorithm is actually going to take care of this for us. It's not going to be that big of a deal. It will just skip the extra duplicate edges. Jeff Goldblum's already been visited. If we're visiting the neighbors of Jeff Goldblum, we've already visited Jeff Goldblum. It's going to be marked as visited and just skip it. So we do get away with this, but I do want to clean this up a bit and make this a little bit better. So instead of just iterating over the cast and the cast, so getting all n squared pairs of cast members, including the cast member to themselves, we can do this a bit better. Is what I want to do instead is I'm going to iterate over the indices of the cast. So I'm going to say for, let me just type this out. Normally I already did my for int I equals 0, I less than uh, movies dot no movie dot get cast dot size I plus plus, and then on my inner loop, so I'm going to iterate over the indices, but I want to make sure I don't duplicate any data. So for each movie, if I only iterate over or each cast member, I only iterate over the cast members that come after it. So when I'm going through this first movie, at index 0, I'm going to get Sean Patrick Flannery, and then I want to iterate over just the remaining actors. So in my outer loop, my first loop, I'm iterating over the indices, and then for each actor, I only want to do the ones that come after it. So just these 3. Then when I get to Lance, I want to iterate over just these 2, and when I get to Jeff, I want to iterate over just Brandon. When I get to Brandon, I'm not going to iterate over anything else. And if I do it that way, I'm going to exactly get every pair of actors exactly one time, which is just a lot cleaner way of doing this. So to do that, I can do int. I can do int j equals I plus 1. So the next index after that, j less than movie dot get cast dot size j plus plus. Then I'm going to get string cast member equals movie dot get cast dot get of I, and then cast member 2 equals movie dot get cast dot get at j, and then add the edge. Now when I run this code, it's going to be a lot cleaner graph. I'm going to have, let's go back to Jeff Goldblum, and Jeff Goldblum has exactly just the other actors in it. Doesn't have himself, doesn't have any duplicate information. I have just exactly the information I want, nothing extra, nothing missing. So it's a much, much cleaner graph. Now, like I said, both ways are going to work for our purposes for the homework, but this way is a lot cleaner. And when you have applications in the future where the algorithm isn't structured in a way that's going to take care of your extra data, you're going to want to do something cleaner like this, something that's going to represent exactly the data that you want. Okay, and that's everything I wanted to cover. Does anybody have questions? If there are questions, I'll hang out more, but I got through all the slides, talked about the algorithms, gave away how to generate the graph. It's up to you to take that graph and run breadth first search on it, take what I walked through in lecture, and then do breadth first search on this graph. So any questions on that, I'll give it a minute. If not, that's been 116. If you need the final exam, good luck on the final. That's it for lecture, though. And good luck on finishing up the tasks. Office hours next week. I think I'll hold mine. Like, technically, the semester will be over next week, but I think I'll hold mine. I'm still deciding. But me and the T's will still be watching Piazza for sure. And if there's demand, I'll probably hold mine next week. I haven't fully decided quite yet. Definitely holding mine this week. Yeah, all right. Take care, everyone. I'll do the 11 a.m. lecture, but this is the last 8 a.m. lecture of the summer. Enjoy the rest of your summer.